soup can labels. If we take this soup can label that's at some point X, and we cut it and we put it on the table, we're going to get a rectangle. So we just need to find out what is the area of that rectangle. Well, we know how to find the area of a rectangle generically. It's just going to be the length times the width. So we just need to figure out what are the width and the length of this rectangle that we obtained by taking this cylindrical shell, this soup can label, and cutting it off the can and laying it on the table. Well, first of all, what's the height of this piece of, whatever we want to call this here? What's the height of this rectangle which we obtained by taking out this cylindrical shell? This, by the way, would correspond to that little green line that we drew when we did the last example. It starts down on the y-axis, and it ends up on the graph of y equals f of x. So what is that height? It's f of x, right? It's the value of y, right? Because this height is y minus 0. But because that point on the top is on the graph, y equals f of x, that height is exactly f of x, where f of x is whichever function's graph you're using to generate this cylindrical shell object. So that's going to play the role of my height, or length, I guess, is what I called it in this formula.
Are we using the same thing? The same.
I'm about to, yeah.
Oh,
As soon as
this isn't from that.
this shape is not the same as the one we're about to do, but
Okay.
the idea, the method, the shell slicing method is the same as we will use. But then what's the width of this rectangle? How do you find out how long a soup can label is? It's the circumference of this circle. So this is why the shell method is, in some respects, a little more interesting. That we're measuring the circumference of that circle, that shell that we cut out of the middle of this thing, circumference. And what is the circumference of a circle? Here comes a geometry formula again. If our circle has radius r, what's the circumference? 2 pi times r. By the way, that's the same as the derivative of pi r squared. Noodle that one for a minute, derivative with respect to r. Okay, but then that means we need to know what the radius of this circle is. And the radius is something that, again, we have to measure from our axis of rotation. But if we do, we find it right there. There's my radius. And so what is my radius in this example? It's x. Because that's the point that we went out to here. So the circumference of my cylindrical piece here is 2 pi x. So that's the width of my rectangle when I lay it out on the table, and therefore the area is 2 pi x times f of x. Does everyone have a grasp on where that area formula came from? So we had this soup can label, the cylinder, in the middle of our solid of revolution. We take that cylinder out, we cut it, and we lay it on the table. It becomes a rectangle. The height of that rectangle is exactly the value of f of x, where f of x is the boundary of the top of the region that we rotated. And the width of that rectangle is the circumference of the circle that we took out. And to know the circumference, we needed to know what the radius was. And there's where we measured from the axis of rotation out to our shell. And in this example, at least, that was x. So the area is 2 pi x times f of x. So then all we would have to do to get to the volume, once we know the radius, and the radius was x, we know the height of one of these shells, and that height was f of x. And the area was 2 pi x times f of x. So what do we have to do to get from that area to the volume of this solid of revolution? Calculus. Just integrate. From x equals a to x equals b. So instead of finding the area of a circle or a washer and integrating that, here we're finding the area of this cylinder, this label on a can, and integrating that. So our integral becomes 2 pi x f of x with respect to x. And that's the method of cylindrical shells. The setup for it, anyway. So let's reimagine this region. Instead of slicing perpendicular to the x-axis here, let's use the cylindrical shell method, by which we're now going to take a horizontal segment inside of our region and think about what it would look like to revolve that horizontal region around my axis of rotation. So take this out of our diagram now, and it's going to become our soup can label. It's like this. And so again, we need to know first of all, what is the height of our rectangle? That's this height right there. Let's start with that. So how would I find out the height of this rectangle, the width of that orange line? Well, we need to put down some coordinates again. We need to decide where our slice is, how we are going to speak of where our slice is. But our slices are not now at different values of x. Our slices are at different values of y, right? Our first slice, our innermost slice, is going to be here at y equals 2. And then as we take more and more slices to go through our figure, we're eventually going to stop when we get to the slice that's on the top. And what is the slice on the top? Y equals 6. How'd you know it was 6, by the way? Because it's on the line y equals x, and our region goes out to x equals 6. And the point on the graph of y equals x that's at x equals 6 is also at y equals 6. So sometimes it helps to put the coordinates on the boundaries of your region so you know what you're up to here. So now when we do this integral, our integral is going to be an integral not taken with respect to x, but rather taken with respect to y. So that's the first difference you notice when we swap washers for shells for the very same solid of revolution, is that instead of your integral being with respect to x, your integral is with respect to y. You change the variable of your integration if you change your method. And that can be a useful thing, or it can actually be a harmful thing in some cases. But for this particular example, I think it's going to be a wash. Either way, it is going to be equally straightforward. But then that means that when we take our integral is going to be taken with respect to y. So it's qualitatively going to look a little bit different than it did before. Okay. So if our slice is taken at a certain height, a certain y value, y, then how am I going to know the height of this slice? So here, let me draw once again. When I'm measuring this out, I want to go out to the right-hand edge and to the left-hand edge, and at each of those, we're going to get some value for x. X equals something over here, and x equals something over there. What is x equal to on the right-hand endpoint? X equals 6. Why is that always the same for every slice?
It's a linear line.
Yeah, it's a vertical line. In fact, that the right-hand side of our region always has the same x value. So x equals 6 is the outside of our region. What's the inside? What's the x coordinate at that point?
3.
Well, in our particular example, it looks like, 3 looks like it might be about there. But again, here we're going to have different x values depending on where we are along this line. But we do know that this point lies on a graph that has what equation?
Y.
Y equals x. Right. So the x value at this point is going to be y. And if that's the case, So if my little line segment here goes from y to 6, how long is it? 6 minus y. And so that's the height of our rectangle. So these are some of the subtleties that creep in when you are setting up integrals for problems like these, is that you really have to be conscious of the geometry. What lengths are we really measuring, and how do we measure them on our coordinate system? So it's not as simple, unfortunately, as just taking the formula for cylindrical shells or the formula for washers and just turning a crank and getting it, because we need to be able to put all of those radii and heights and stuff into context. So in this example, the height of one of our shells is 6 minus y, if that shell is taken at a y-coordinate of y. Okay, so that was the first step, is we needed to figure out the height. Now let's get at the width of this rectangle, which is the circumference of this shell, which is 2 pi times the radius of that shell. So now we just need to find what is the radius of this cylindrical shell. The radius is measured from our axis of rotation out to the edge. It's 6 for the biggest shell. For the outermost shell, it's going to be 6. But in general, what is that radius? This one we can't overthink too much. It's the distance from the x-axis, which is our axis of rotation, out to our shell, and our shell is at the coordinate y. So we're going from 0, which is our axis of rotation, out to y, which is our shell. So what's the length of that line segment? Just y. The picture gets a little cluttered kind of quickly here, but the radius of that shell is y, and so our circumference of that cylindrical shell is 2 pi y. Whew. So the area of the cylindrical shell is 2 pi y times 6 minus y. And therefore the volume is the integral of 2 pi y times 6 minus y, with respect to y, from y equals 2 to y equals 6. Now we remember what the volume was when we did this with the washer method. What was the volume of this volcano? Yeah, 160 pi over 3. So if there is any justice in the world, we should get that same answer when we evaluate the cylindrical shell integral. Let's do it. Just so that we can sleep well tonight after you've, finished those homework problems. Okay, so we can bring the 2 pi outside the integral because it's a constant multiple. Y times 6 minus y, before we integrate it, ABC, algebra before calculus. So this is 6y minus y squared. Antiderivative for 6y. 3y squared, great. Antiderivative for y squared. And then I'm evaluating that from 2 to 6. So I get 2 pi out front times 3y squared when y is 6 is going to be 72. 1/3 y cubed when y is 6 is going to be 50. Wait, what was it? 216 over 3, 72. Oh, that's interesting. Then I'm going to get minus 3y squared. And when y is 2, that's going to be 12. And then plus 8/3. And now I'm getting concerned that I did some arithmetic wrong. So what did I screw up here? There we go. So 108 minus 72 minus 12, that's 108 minus 84, that's 24. So I have 24 plus 8/3 times 2 pi. 24 plus 8/3 is 72 plus 8, that's 80. Oh, look at that. Sure enough, that's 160 pi over 3. Yay. When the dust settles, we get the same answer for this volume.